Okay, so in this practical session, we're going to go through an example that uses simulated data based on an outcome HbA1c, which is a measure that's used to diagnose diabetes. So really, this is a measure of this is a study that's looking at diabetes outcomes across society. This is based on a paper that is a tutorial. And there's a link to that in this document. So if you want to kind of know more about this and see it in a bit more detail, do go read that paper. So we're first going to load some packages, and then we're ready to load the data. So I'm going to run this line, which reads in the dataset, which is a .dta stata file. So this reads that in, and we can now look at that data. And we can see we've got our HbA1c, our outcome, and then we've got that binarized into whether someone is diabetic or not. We're not going to use that variable. We've then got 5 different variables which are going to define our intersectional strata. So we're going to be looking at inequalities between combinations of these 5 variables. The next thing that we're going to do is create our strata level variable. So this is going to create a unique identifier for each combination of those 5 variables. And we're going to do that by saying that each variable can be defined based on one number in a kind of 5-digit number, where the first digit represents sex, the second digit represents race, the third education, the fourth income, and the 5th age. So if I run this code, we will see that in this data set, we've now got this new data set, new variable, which basically mushes together these 5 numbers into a single code there. Next thing we're going to do is import our value label. So at the moment, each of these variables, we can see this here, are variables that have character labels but aren't themselves characters. So what we're going to do is turn these variables into factor variables using the unlabeled command. So if I run that, you can see these are now appearing with labels that kind of make sense. So we can see that stratum 21114, the 2 represents female, 1 represents white, 1 represents less than high school, 1 represents low income, and 4 represents age 60 plus. We might at this point want to do a little bit more investigating of this data, so it might be worth making a table of our strata. So we can see from that some of our strata have quite small numbers, even some that have only 1 observation. Other strata have a lot more, into the quite high hundreds. And that's pretty normal for social data, where often some of these combinations of these 5 variables are relatively rare. We could add that to our data set as a variable if we wanted to. So if I run this code, we're saying we want to group by stratum and then create a new variable called strata n, which is the number of observations in each stratum. And so that's now appeared there on the right-hand side. We could also look at our independent variables, our variables that define our strata, get a sense of the number of observations in each, check these make sense, so check that we've got kind of similar-ish numbers of men and women, check that these proportions look how we would expect for the population that we're looking at, check that our factors are what we're expecting. So this is based on American data, where the division between white, black, and Hispanic probably makes the most sense. We've got 4 categories of high school education, 4 categories of income, and 4 categories of age. We probably also might want to get some summary statistics of HbA1c, check that these look kind of how we might expect in our data. And we might also want to plot that outcome variable in a histogram. So what we've done here is use ggplot, told that we want to use data where the variable we're looking at is HbA1c. We want to make a histogram, We've converted that X variable here to a percentage. And then we've got a few kind of aesthetic things that we've added to this graph, such as the maximum, the minimum, the sample mean, etc. Okay, we're now ready to start our modeling, and we're going to start with our initial model, which is our null model. So this is the model that contains no fixed part X variables. We've just got our outcome and our random effects. So we're going to use the command LMER, which is in the LME4 package. It stands for linear mixed effects regression. We then specify our outcome variable, HbA1c. And then on the right-hand side of our equation, we've just got our strata level random effects. So we're saying we want these random effects defined by strata, and the thing that we want to vary is the intercept represented by a 1 there. And we're saying what data we're using and running that model. We'll look at the output for that in a second, once we've run our second model as well. We can make predictions based on this model. So I'm just using the predict command that will make a prediction for each of these, each of our strata based on the fixed part of our model, which at the moment doesn't have much in it, and the random level 2 part of our model. Next, we can run our second model. So this is the model that's the same as our first model, but we've now added in the additive effects of our strata variables. Okay, so it's the same code as model 1A, but we've added in code for sex, race, added in variables into the fixed part of our model there. These are already factor variables, so R will automatically know to treat these as factor variables, as categorical variables. It will remove one, add dummy variables for each category minus a reference category. Run that. So we can now make some predictions. I've already done this. This takes a minute or two, so I'm not going to run it again. We're using the predict interval command, and this is a really useful command because not only does it give us predictions, as the predict command does, but it also gives us confidence intervals around that prediction. So that's a really useful kind of feature of this. And that produces a separate data frame, where for each observation, we've got a different prediction and a different upper and lower bound on that prediction, along with an ID there. Actually, no, the ID we add on later. So the ID we add into this data frame here, using the mutate function here. This is going to allow us to merge this into our original data. So I'm going to run this to add that ID variable, which, as I said, I've already done. I'm going to do the same with our data set, create that ID variable. And then when we merge these two together using the merge format, we can just say merge the original tutorial data set with those predictions by this newly created ID variable. And then we're just going to rename some variables just to make it clear that which model these are based on. So we're just renaming that variable called fit, M1B M fit, and the same for the confidence intervals. The next thing we're going to do is create a new data frame which has data just at the stratum level. So at the moment we have this big data frame which has an observation for each individual. But now we've got these predictions, we don't actually need that level of detail because actually all the predictions for anyone in a single stratum are going to be the same. So we're going to collapse this data down to the strata level. So we're going to create a new data frame called stratum level. And to do that, we're going to aggregate our variables. So any variables that change in our data set, we need to include here. At the moment, that's just that we're interested in that just HbA1c. And we're going to do that by any variables that don't change within stratum, which is pretty much all of our other variables here. Okay, let's have a look at our model outputs. So I'm going to use tab model to display these because it presents them quite nicely in a table. We can see that here. So you can bigger. There we go. So we can see here we have in the first model an intercept of 40.79. That's effectively our mean value of HbA1c across all stratum. In that, we've got a level 2 variance of 9.37. That's the variance between strata. And a level 1 variance of 90.26. That's the variance within strata between individuals. So we can see about 10% or about 9% of this variance is occurring at the higher level. So that's our estimate of what's labeled here as the ICC, intra-class correlation, but it's also the variance partitioning coefficient, the VPC. Those two things are equivalent. And then we add in our main effects, and we can see these are kind of statistically significant in the directions we'd probably expect. So women have a lower risk of diabetes than men. Black and Hispanic people have a higher risk of diabetes than white people. More educated people have a lower risk of diabetes. High income people have a lower risk of diabetes. And older people have a higher risk of diabetes. We can see that by adding in these main effects, our level 2 variance has been substantially reduced. Okay, it's gone from 9.37 down to 0.88. So that's a reduction of the level 2 variance of about 90%. So our PCV, our proportion change with the variance, is about 90% here. So most of our variance is explained by those additive main effects, but there's still a substantial chunk that's unexplained, that 10%, which is a result of multiplicative combinations of these variables. 90% is about standard, I would say, for most MAIHDA analyses in health. That's the kind of area that we get. So if you're finding PCVs that are lower than that, 80%, 70%, that suggests quite a lot of multiplicativity. If you're finding PCVs of 95%, 98%, that's perhaps suggesting there's not so much multiplicative going on as additive stuff really is the kind of the dominant in what produces these intersectional differences. So it now might make sense to make a plot of what our model is predicting for our residuals, for our strata. So to do that, what we're doing is we're taking our strata level data set. We're going to create a variable which will give us a rank of our predictions. So if I run that, I just have a look at that stratum data. You can see we've got our model 1B predictions. Those are our predictions from model 2. And then we've got the rank of those predictions on the right-hand side there as well. So we can then make a plot of our of those predictions against that rank. We're going to do that as a point graph and then provide a range around those points that give us our confidence intervals. So if I run this code, that gives us this graph here, which is perhaps quite difficult to interpret on its own. It kind of gives us a sense of that there are some strata that are predicting quite low, other strata that are predicting quite high. It gives us a sense of the range, but it's quite difficult at this point to kind of say what each of those strata are. This graph doesn't have labels for each of those points. It might be sensible to look at which are the highest and lowest stratum. So the highest and lowest predicted stratum. So we're going to sort by rank and then look at the top and bottom, in this case, the top and bottom 6 stratum. And from this, a few things are kind of popping out, I suppose. You can see that the majority of those top ranked stratum, the lowest at risk. These are the people down here. They're mostly white, they're mostly female, they're mostly college educated to some extent, they're mostly high income, and they're mostly young. Okay, so we can see that the most advantaged groups tend to have those characteristics. The least advantaged groups are quite mixed in terms of their sex, but they're all Black. None of them are fully college educated. They're all old, or older than 60. So we're kind of seeing by looking at these the kind of variables that are perhaps really dominating in terms of what's going on with these strata. It might be that we're also interested in just looking at the multiplicative effects. Okay, so these are the effects on top of those additive effects. So we know that there are additive effects that we saw in our output here. We saw that there were an effect of sex, an effect of ethnicity, and so on. And those additive effects would suggest something about the predicted values of HbA1c. But we also know that there is something additional on top of that as well. So we might be interested in particular in plotting those individual, those multiplicative effects. And we can do that using the RESIM function, which extracts the random effects from our model. And then the plot RESIM function will automatically plot those as well. So if I run this, I've already run the first line. So if I now run this plot, okay, there it is. So we can see in this plot there are a few strata which seem to be less disadvantaged, more advantaged than we would expect given their combination of additive effects, and a few strata that are more disadvantaged given the additive effects. This again is a graph that's quite difficult to interpret. We can see that most strata conform approximately to their additive effects, but the ones that are highlighted are coming out as statistically significantly different from those. But we probably want to identify which ones those are. So we're going to now make a plot that just highlights those that are statistically significant. So we're going to use what comes out of this plotting process. So when we do this, within this plot object P, we have a lot of data, and we can extract that data, and included in that data is data about statistical significance. So we can first extract that data. We can then filter it so that only the statistically significant strata are included. So filtering based on significance being true. Run that. And then we can plot just those strata that have statistically significant multiplicative effects. And I've added, in doing this, I've added in the labels of those strata as well. So we can see that strata 22114 is particularly advantaged. Okay, that strata seems to be particularly advantaged in terms of its risk of diabetes, has a generally lower level of HbA1c. It's a bit bigger. And this strata 21223, we can see that that's particularly disadvantaged. That's a strata that has higher levels of HbA1c than we would expect.